So when writing this test, I had to consider how much material you have. Test 2 is going to go from 4.1 to 6.4, and there's just more stuff there than I can reasonably test. So one of the things I'm going to tell you right now is 4.2, which you guys really didn't like. I'm not going to be testing on 4.2, so you can concentrate on some other things. But let's take a look. I'm going to blend a couple problems from 4.1 and 4.3 for this first example. So it talks about people who use drugs or not use drugs and who tested positive or not tested positive. If you're doing this kind of stuff for yourself at home, what I strongly suggest is that you add up some numbers, like 61, 46, that's going to give me 107. I'm not sure why this isn't writing better. And then over here we got 54 and 53. And it's really heartening to see that these add up to the same thing each way. So a little double check on your work. Let's remind ourselves of some notation. If U is the event that a randomly selected person from this table is a user, what does U bar mean? Yeah, they're not a user. All right, it's the complement. So, not a user. And then if N is the event that a randomly selected person tests negative, what's N bar? Yeah, positive test. Let's look at a couple probabilities. Eventually what our goal is going to be is to try and decide if a couple of these events are independent events or not. So we'll start with probability of U. What's the probability that somebody in this table, selected at random, uses drugs?
54 divided by 107.
Yeah, there's 54 users over 107 people here. Now one thing that will get you an easy 0 points is if you forget the denominator. If you just give me 54, that's clearly wrong. Probabilities have to be between what two numbers? 0 and 1, absolutely. So if you come up with something outside of that, there's something wrong, go back and fix it. How about the probability of somebody testing negative?
46 divided by 107.
Yeah, 46 over 107. Thanks, Matilda. Let's change things up. What does this notation mean? Given. That bar there, and I should probably make that a little bit more of a vertical bar, stands for given. It's a probability of somebody using drugs given that they tested negative. So that given stuff changes the sample space. And let me kind of address things this way. For this probability, I'm only working with part of the table. I'm working with the part of the table that tested negative. So that's this part right here. So let's just circle this part. Our sample space has been reduced from this whole table down to this little bit. So instead of 107 users, now we got 46 people in our sample space. Of those 46 people, how many of them use drugs? 12. And it doesn't have to be illicit drugs. It could be anything. It could be medication, etc. So this is nothing bad or condemning. So 12 out of 46. How about the probability of U given N bar? Well, N bar essentially means that they tested positive, right? That they didn't test negative. If you didn't test negative, then you tested positive. So now we're at this part of the table, right here. What's the probability that you tested, or that you're a user, given that you tested positive?
42 divided by 61.
Yeah. 42 users tested positive out of the 61, or 42, yeah, 42 users tested positive out of 61 that tested positive altogether. So 42 over 61. Now, generally speaking, I'm happy to see things left as fractions. I don't necessarily like decimals for these types of answers, but for our convenience, let me give you some percentages. This first one is 50 0.47%. The second one is a little bit less than 43%, so 0.42. I think is it 89 or is it 99? 99. Thank you. Then down here, 0.2609 and 0.6885. So the question is, are these two events independent or are they dependent? Is there some relationship between using and testing negative? Well, let's take a look at two probabilities in particular. Let's take a look at these two probabilities. Probability of being a user, just over 50%. But if I then tell you, oh, well, they tested negative, does that change or affect this probability? Yeah. If it didn't, they would be independent. Then whatever happens here doesn't affect what happens here. They'd be independent. But because the knowledge of this result changed this probability, they're dependent. So U and N are dependent because the outcome of N changes the probability of U. You can see that down here. If you find out that somebody tested positive, they're much more likely to be a user than if they tested negative. But either way, whatever outcome of N you get, it's changing the probability that somebody is a user. So they're dependent. If there was no change in those probabilities, then they would be independent. Okay. Let's do one more thing here. The odds against you. What are the odds against somebody being a user here? Well, odds against mean the number of ways that it can't happen versus the number of ways that it can happen. So let's write that down. Can't versus can. And let's look back at our table. How many ways can't it happen? Well, there's 53 people who aren't users. So that'd be 53. Ways that it can happen would be 54. So almost even money there. But those would be your odds against. Odds for would just be the reverse of that. There you go. So there's a little bit of review from 4.1 and 4.3. Like I said, we're going to skip 4.2. But there is one more thing from Chapter 4 that we need to take care of. And that is, let's see, put this aside here. That other thing is counting rules. There were several things that we did in order to count. We had kind of a multiplication rule, like what you would find here for that first problem in section 4.4. This actually comes from one of your homework problems, although I made it a little bit more user-friendly. Radio stations have call letters that begin with K or W followed by 3 letters. So something that looks like this. Okay. How many possible combinations of these call letters are there? Well, you can use these letters more than once. But in our first call letter, we have to have either what? A K or a W. So there's only 2 choices. How many choices do I have for the next one? 26. And then you can repeat those, so it's 26 again and 26 again. Hopefully when you plug this into your calculator, you're going to plug it in as 26 cubed and then multiply by 3, or excuse me, by 2. So 35,152. in your homework you had a problem like this, except the radio stations could have call letters that had either 2 or 3 possible 2 or 3 letters after this. So in addition to calculating this, you would also have to calculate 26 times, or 2 times 26 squared, and add that up. So what? 2 times 726, 776, so 1340, 1352, and then add it here. A lot of what I'm going to test comes down to these next couple examples. And there was 2 things that we had to deal with. One was permutations, and the other was combinations. What's the difference between permutations and combinations?
One of them has to go in order, and the other one doesn't matter. Permutations is order, combinations is
Order matters. Order doesn't matter. Okay. Order matters, order doesn't matter. When you're playing the lottery, do you have to match the numbers that they draw in order, or is it just enough to match the numbers? Just enough to match the numbers. So when you're playing, say, for instance, Luck for Life, and you've got to match 5 out of 48 numbers, is that going to be a permutation or a combination? Combination. So you should start out like this: 48, choose 5, and then we also have to match a number called the lucky ball, and that's selected from 1 to 18. Yeah, basically 45 times 18. You could do 18 choose 1, but 18 choose 1 is just 18. So let's just do 18. So 1.71 million, so 1,712,304. You remember how to do this on Google Sheets? The calculation is up here. It's combin. It'd be 48, comma 5. Gives you this times 18 for a very nice, neat 30,821,472. Yay. So that's an example where the order doesn't matter.
Quick question.
Yes, please.
Where did that 30 million come from?
That's
Number you would want?
that's the product of this times this. This times 18.
Okay, thank
So the first one is your 48, choose 5, and the second one is times the 18. So let me put a little, I'll kind of be consistent. This, and this are all the same thing.
Okay, thank you.
Yeah, thank you. Let's move on down to the one below that. The starting 5 players plus the goalie for a total of 6 are going to stand on the blue line for the national anthem. How many different ways can they arrange themselves? Well, we're not choosing like 2 out of the 6 or 5 out of the 6. We're choosing all 6. So it comes down to how many different ways there are there that you can arrange 6 objects. What tells us that? Yeah, well done. Who got that? Oz? Nicole? Well done. 6 factorial, and Oz is going to derive me for that. That's 720. You have to type in on Google Sheets, you just type in fact and then M. That'll give it to you. But let's change things up a little bit. If there are 20 players on the bench and you're going to put 6 of them out on the ice for the national anthem, how many different orders can you put those 6 players in? There's something you got to be... How many orders? So am I saying order matters or order doesn't? It matters. If order matters, then what do we got to do? Permutation. So it's going to be 20p6 And that's going to be a pretty big number. I don't think the NHL has enough seasons to take care of all the possibilities here. 27,907,200. What if all you cared about was the 6 players you put on the ice? How would that change things? Lizzie, what do you think? If I just said, well, throw 6 players out on the ice, I don't care who.
Then you would use combinations instead.
Yes, you'd use combinations. So it'd be 20C6. There's going to be a lot less of them. 38,760. Nice. Nice. Comments on these?
Question.
Yes, please. Larissa.
Um,
Lisa, sorry.
thank you. For the factorial 6, the probability be 1 out of 720, right?
Oh, yeah, there's a part B here, right? So with the probability that they're in alphabetical order, yes, that'd be 1 out of 720, because there's only one way they can be in alphabetical order.
Okay.
Right.
Thank
I'm assuming they have different names. Yes. Well done. Thank you. All right, this next part is going to require a little bit of Google Sheets work. So let's take a look at that. I'm going to remind you I'm calculating the mean and standard deviation of some numbers. Probability distribution, I should say. So if you wanted to follow along, then this is what you should type into your Google Sheets. Type in the numbers 0 through 5 in the first column. So 0, 1, 2, 3, 4, and 5. And in a second, I'll read off the probabilities. So get to the top of column B. And type in the following probabilities. 0.662 for the first column, first cell, or excuse me, second column, first cell. 0.285, 0.048, excuse me, yeah, 0.048, yeah, I said that right. 0.004, 0.001, and 0. Now, if this is actually a probability distribution, how can I check it? How can I make sure that, yeah, this is actually a probability distribution? What should I see? They add to 1. So if you do sum of all those, and it's even suggesting that, yeah, it gives you 1. Now, if it was 0.999 or something like that, then it's probably a rounding error. If I gave you a problem like that I really wanted to test you, it would be noticeably off from 1 if it wasn't a distribution. There's a couple things we want to calculate. We want to calculate the mean first. So I do expect you to know how to calculate the mean. Let's go over that. So for the mean, I want to do x times p of x, and then I want to sum that up. So the sum of x times p of x is going to be the mean. So let's calculate that. The mean also goes by the name of expected value. Those two are interchangeable. At the top here in column C, type equals. Click column A1 times B1. And yeah, you get a very predictable result of 0. But we're not doing that just to get the 0 there. We're doing that to set up the rest of our calculations. Now, are you going to sit there and type in that calculation for all 5 of these remaining cells?
No.
Click and drag. Grab that little circle, drag it all the way down.
Why is it not tabulating it?
And then you want to sum that up. You should get 0.397. Now, I haven't really decided here about the second part of this, but there's another part that we need to do in order to get the variance. For the variance, I'm going to need this column. It's going to be P of x times x minus mu squared. And the sum of that is going to be the variance. So sigma squared is going to be equal to the sum of P of x times x minus mu squared. Now there's something special about this calculation that you have to be careful of when you're doing Google Sheets, unless you wanted me to get really tricky and fancy, but this is a course in statistics, not in Excel/Google Sheets. So this was 0.397, is that right? When you type in this, actually type in the number 0.397 when you do this calculation. Otherwise, if you try and get a little tricky and click the cell down at the bottom, it might screw things up for you. So let's go to this next column. Equals P of x. What column has P of x in it? B. Times left parenthesis x minus the mean. Now type in the mean. Type in 0.397. You don't need to type in the 0 if you don't want to. Followed by a right parenthesis, shift 6 to get the square key, like that. Now I'll let you look at it there for a moment. Once you get that one all set, it should probably ask you, hey, do you want to do the same thing for the rest of them? Sure. Well, it didn't for me. Maybe it did for you. And drag it all the way down. The sum of that is going to be your variance. So it's going to be 0.371391. Oz, I'll be happy to help you out with it afterwards. Ryan, question?
Can you repeat how you got the 0.379?
You need to add up all of these. So you want to add up that column. All right? That's your variance, that 0.371391. But if I need the standard deviation, what do I do to get the standard deviation? Ian, back?
Well, I got 0.361 for variance.
Did you grab all of these? I'm pretty sure, are most of you guys getting 0.371391?
Yep.
Okay. It's probably just a small typo. If you want to come up afterwards, you know, with Oz, we'll figure it out. Now, that's the standard, that's the variance. How do I get the standard deviation? Square root of the variance. So do equals SQRT, parenthesis, and then just click the cell. That's going to be your standard deviation. So standard deviation, sigma in this case is 0.6094. Great. Let's determine using the range rule of thumb what values are significant, what values aren't significant. And I'll remind you that, you know, significantly low starts at mu minus 2 times sigma, and significantly high is going to be mu plus 2 times sigma. So I want to do both of those calculations. High. So let's do both of those. I'm going to start with equals 0.397 minus 2 times, I'm just going to be lazy. I'm going to come over here and grab my sigma instead of typing it in. 0.397 minus 2 times sigma. That's significantly low. And I want to do the same thing for significantly high, so equals 0.397 plus 2 times sigma, which is up here. So significantly low and significantly high are these numbers. So negative 0.821 and 1.61. Let's look at what that means for our experiment here. So we've got 0, 1, 2, 3, 4, and 5. Significantly low started down here. Let's see. That's where our cutoff for significantly low. Significantly high was about right here. So we had negative 0.8 and was it 1.61 or 1.6? There's your significantly high. Can we get an event that's significantly low in this case? No. It's less than the smallest number we can get from this experiment. Significantly high would be all these values, 2, 3, 4, and 5. Of course, there's no chance of a 5, so it's just really 2, 3, and 4, but you're applying the range rule of thumb there. Yay. Whew. Now, that's a lot of work in order to calculate the mean and standard deviation. There's a shortcut that you can use in the case of section 5.2. So this is really from section 5.1. Section 5.2 talks about binomial random variables. So binomial random variables. A lot of times it's got notation like this. Binomial of n and p. N is the number of trials. Number of trials. Does anyone know what P is? Yeah, probability of success. And just as a reminder, Q equals 1 minus P. Now, in order to have a binomial random variable, it has to pass the fits test. Fits, F stands for fixed number of trials. So let me do that up here. F is fixed number of trials. What's the I part for? Independent. 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 Sorry. T. Two outcomes. And S is your same probability of success throughout the trials, that it doesn't change. So flipping a coin or guessing randomly on the SAT, etc. If you have a binomial random variable, this calculation of the mean and standard deviation gets a lot easier. A lot easier. The only thing I caution you of is that you make sure you only use it for a binomial random variable. It doesn't work for any other random variable you're going to encounter. But for a binomial random variable, mu equals n times p. On average, that's what you're going to get, n times p successes. The variance is the square root of n times p times q. The q, of course, is 1 minus, I said the variance, standard deviation. The variance would just be n times p times q, or n times p times 1 minus p. Let's remind ourselves what one of these calculations might look like. What's the probability that amongst 20 tosses of a coin you can get exactly 14 heads or more than 14 heads? Okay. Let's do a couple calculations here then. Is tossing a coin 20 times a binomial random variable? You get a fixed number of trials. Yeah. Is the result of one toss going to affect the result of the next toss? They're independent. Two outcomes, heads and tails. Same probability of success, 0.5 throughout the trial, so we're looking good. Now keep in mind that you will be given the commands on the top of your exam. So you want binomial distribution, X and P, and then false. Let's do that one together here. Let's see here. I want to go here, and let me open up another sheet. I'm going to be a little bit fancy here. Let's start out with a 0. You could have 0, 1, 2, 3, etc. I'm going to be lazy. I don't want to type in all these numbers. So what I'll do is I'll do equals this one plus 1. Now it might seem kind of simple, but here's the cool thing. Once I set up the first one, I can click and drag all the way down. Let's drag all the way down to 21, I guess. There you go. So there you go. Those are all the different things that can happen. Those are the different number of heads you can get when you toss a coin 20 times. I want to do equals binom distribution. Number of successes. That's this one. Comma. 20, because I'm flipping a coin 20 times. Probability of success, 0.5. And then false. And I'm going to copy that all the way down. How can I check that I got this right? Yeah, equals the sum. And the sum should equal 1. And it does. Great. Let's look back at the actual problem here. What's the probability that you get exactly 14 heads? Well, that would be right here. Exactly 14 heads. Great. So exactly 14 heads would be about 0.0370. What's the probability of getting more than 14 heads? The thing you have to pay attention to is, does that include the 14 or not? No. So if you want more than 14 heads, you've got to add up these probabilities. So let me just go over here, equals sum of these probabilities starting at 15. Bless you. So about a 2% chance, 0.0207. Nice. Nice. The rest of what you can expect is just some calculations of areas underneath here. There is one last final thing that I'm going to remind you of. I mean, you should be able to find areas for the standard normal curve or a non-standard normal curve. But the notation that you need to know and make sure you've got down for Thursday is this one right here. Z sub alpha. As a reminder, Z sub alpha is going to be the point in the normal distribution with the area equal to alpha in the right tail. So if I wanted the area to be 0.025 in the right tail, Z sub 0.025, how much of the area has to be in the left tail if 2.5% is in the right tail? 0.975. So to get this number and to figure out where you are here, you would do norm inverse, not of the 2.5%, but of the 0.975, and the mean and standard deviation. That's going to give you this point, which has 97.5% of the area here and 2.5% of the area in the tail. It should be about 1.96. if you did it out on Google Sheets. Okay, the rest of it we did go over. Make sure you expect some problems from 6.3 and 6.4. The ones from 6.3 are really limited. It's just kind of, you know, what are your biased and unbiased estimators? Have a good one and see.